Hello and welcome. This is Caroline Annis, Mike's wife, and you're listening to episode 92 of the Space Rocket History Podcast. Mike has been sick all week and unable to speak without coughing, but he didn't want to miss an episode, so he asked me to fill in. So please bear with me, and I will do my best. Hopefully, he will be able to record next week's episode himself. Now let's begin episode 92, entitled Soyuz Development. Soyuz is a series of spacecraft designed for the Soviet space program by the Korolev Design Bureau in the 1960s that remains in service today. The Soyuz succeeded the Voskhod spacecraft and was originally built as part of the Soviet manned lunar program. The Soyuz spacecraft is launched on a Soyuz rocket. The Soyuz rocket design is based on the Vostok launcher, which in turn was based on the 8K-74 or R-7 Semyorka, a Soviet intercontinental ballistic missile. A Soyuz spacecraft consists of three parts, from front to back. First, a spheroid orbital module, which provides accommodation for the crew during their mission. Second, a small aerodynamic re-entry module, which returns the crew to Earth. Third, a cylindrical service module with solar panels attached, which contains the instruments and engines. The orbital and service modules are single-use and are destroyed upon re-entry in the atmosphere. The orbital and re-entry portions are habitable living space. The original mission of the Soyuz design was to perform a circumlunar flight with a person on board. The precursor of the modern Soyuz was the piloted 7K vehicle, which was a component of the Soyuz complex. In terms of design, the Soyuz rocket space complex included a 9K booster unit, 3 11K space refueling vehicles, and the piloted 7K vehicle. After President John F. Kennedy announced to the entire world that the U.S. was accepting the Soviet challenge and beginning its fight for supremacy in space, Soviet conceptual designers came up with the idea of a piloted circumlunar flight using materials on hand, without a super heavy launch vehicle. Mikhail Tikhonravov was one of the giants of the Soviet space program. He played a critical role in almost every major space project at Korolev's Design Bureau, OKB-1, until his retirement in 1966. Korolev approved the initiative that came out of Tikhonravov's design department, calling for the circumlunar flight using materials on hand and requiring at least 5 Semyorka launches. The plan was to launch the 9K booster unit into near-Earth orbit first. Next, 3 11K refueling vehicles would be launched in succession and transfer fuel to the 9K using pressurized gas. The 3 refueling vehicles brought the fuel margin in the 9K up to 25 metric tons. The 7K carrying 2 cosmonauts would be launched last. It would dock with the 9K, and after 1 or 2 orbits around Earth, the 9K boosted it toward the Moon. Before flying around the Moon, the unneeded 9K would be jettisoned. The 7K was supposed to return to Earth by itself and enter the atmosphere at re-entry velocity. In order to execute a circumlunar flight according to such a complex plan, first and foremost, it was necessary to solve the problem of reliable automatic rendezvous and docking in space. The second problem was the development of a new piloted vehicle with a new control and navigation system, ensuring return to Earth within a very narrow spatial corridor using 2 atmospheric passes to reduce the speed. Despite all the complexities of this proposal, Korolev took it to the decision makers. The psychological effect of the flights of Gagarin and Titov on the nation's top political leadership was so great that without a serious technical evaluation, the Soviet Council of Ministers authorized the proposal for a circumlunar flight with a decree on April 16, 1962. The Soyuz program was mentioned by name for the first time in this decree. All 3 spacecraft had been developed in drawings, but the manufacture of the vehicles at the factory was not proceeding well. The factory manager, Turkov, had no trouble proving to Korolev the OKB-1 factory was in no condition to fulfill the programs for Vostok's, Zenit's, and the interplanetary and lunar automatic stations if it was also going to be loaded down with an armada of Soyuzes. Korolev decided to broaden the front of operations, and on December 3, 1963, another decree was issued entrusting the manufacture of the unpiloted 9K and 11K vehicles to the Progress factory in Kubyshev. However, Korolev was unwilling to hand over the piloted 7K vehicle to anyone. The 7K was the most complicated part of the Soyuz complex. Without it, the 9K and 11K lost their meaning. You may recall that Boris Cherkov was the head of the Instrumentation and Controls Department at OKB-1. All of the departments subordinate to Cherkov viewed the development of the control systems for the 7K as a natural continuation of the work that had been started on the Zenits and Vostoks. Here, wide-ranging opportunities for implementing new inventions for automatic flight control really were presenting themselves. Boris Rauschenbach, the preeminent Soviet rocket engineer, headed the department that was tasked with developing a system that would perform the entire spacecraft motion control cycle in low Earth orbit, lunar space, and in the atmosphere during return to the ground. The system would have to support the following: orbital, inertial relative to fixed stars, and solar orientation for illumination of the solar arrays. The system would also have to support various programmed maneuvers, orbital corrections, precise stabilization of the spacecraft during operation of the correcting engine, rendezvous, final approach, and docking with another spacecraft. And it would have to support guided descent to Earth, both from near-Earth orbit at orbital velocity and during return from the Moon at re-entry velocity. The memory of the automatic part of the onboard complex control system would have to recognize set points, the required position of the spacecraft's axes in space, flight delta velocity, and selection of the requisite timeline for activating or deactivating equipment. These set points would be uploaded via command radio link from the ground or from the display and control panel for subsequent execution at the specified time of the in-orbit operations. In addition, it was still possible to make real-time program changes by commands from ground stations and from the crew display and control panel. Nikolai Kamanin, the cosmonaut trainer, and a few other cosmonauts were quite pleased when they were promised that the crew would have the capability for complete functional backup of the control of all operations, including docking and descent. The design called for visual data display on electronic indicator screens and optical sights for the direct observation of external reference points. The control system being designed made it possible, at the discretion of the ground or the cosmonaut, to select automatic, manual, or mixed control modes. Alexei Asayev, the Space Hall of Fame rocket engine designer, developed a brand new approach and correction engine unit called SKDU. It had two engines, a main approach and correction engine called SKD, and a backup correction engine called DKD. The systems of effectors for attitude control and final approach employed highly concentrated hydrogen peroxide. The staff at OKB-1 had developed two systems of effectors, approach and attitude control engines called DPO, and attitude control only engines called DO. A fundamental innovation was the use of an electronic instrument that measured the intensity of the ion flux hitting the spacecraft and generated signals indicating the deviation of the spacecraft's axes from the direction of flight. The ionic orientation system had undergone preliminary testing on Zenits with encouraging results. Initially, the 7K spacecraft had been designed to carry 2 cosmonauts. For that reason, the Vostok landing method was rejected. No ejection seats would be provided. The Soviets believed the Voskhod spacecrafts confirmed that spacesuits were only needed for spacewalks. If a cosmonaut was not performing a spacewalk, he would not get a spacesuit. That was a fateful decision. A descent module shaped like an automobile headlight was designed to ensure a guided descent into a specified area with great precision and acceptable G-loads. For landing, a soft landing rocket-assisted parachute system needed to be developed. An emergency rescue system for an emergency during launch or during the initial flight segment was developed. Soyuz orbital modules would be assembled at the factory for experimental machine building, next to Korolov's design bureau. Upon receiving a command from the ground or an emergency command from the launch vehicle, this system, using powerful solid propellant engines, separated the spacecraft from the launch vehicle, moved it as far away as was possible, and activated the nominal landing system. A habitation module was provided to create additional comfort during prolonged flight. Its forward section contained the docking assembly and airlock hatch. The instrumentation and controls department wanted to consolidate the large number of radio systems into one complex. They developed a long-range radio complex called DRK, which made it possible over a single radio link to transmit individual commands and files of set point commands, to measure orbital parameters and current coordinates, and to ensure the transmission of a television signal and voice communications at distances from the Moon to the Earth. For reliable long-range communications and the transmission of pictures, a parabolic antenna was designed that opened after orbital insertion. A new BR-9 telemetry system was also developed for all Soyuz-type vehicles. In December 1962, Korolev approved the draft plan for the circumlunar flight by a Soyuz, which called for 5 launches and 4 dockings. In 1963, the design departments that were now finished with Vostoks and having started work on the Vostok hoods spent their time developing the new Soyuz descent module and the rocket-assisted parachute landing system. Models of the descent module were subjected to wind tunnel tests. The designers struggled fiercely with the developers of various systems about their weights. The most complicated problems of 1963 were associated with the rendezvous and docking modes. 2 departments contended to develop the docking assemblies: Semyon Shizhakov's design department and Lev Vilnitsky's department of control service actuators and mechanisms. By that time, Vilnitsky had acquired a strong staff of electromechanical technicians, while Shizhakov was extremely busy with the development of instrumentation. After much indecision and debates, it was decided that Vilnitsky's department would handle the docking assemblies. Like NASA, the Soviets found that rendezvous between spacecrafts was another difficult problem to solve. The Soviet ground-based radar guidance was not adequate for the task. It would take an onboard computer for the control system to solve the problem. Unfortunately, in 1963, there was none available. It would have to be developed. In the chain of sequentially solved problems, the onboard digital computer proved to be the most complicated link.
Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange Donate button or the Patreon link. Thanks.